In this lecture, I am going to cover the periodic properties. Specifically, I am going to discuss about the six important periodic properties. One is effective nuclear charge and the relation of orbital energies of atoms in the periodic table, electronic configuration, atomic and ionic sizes and radium, ionization energy, electron affinity, and electronegativity. First, let's discuss about the effective nuclear charge and what is the consequence of shielding effect. So before discussing the effective nuclear charge, we need to understand what is shielding effect and how it occurs in an atom. Let's take this example. See the picture on your right. You have the nucleus in the middle and you got the shells arranged, one next to the other. From n to n minus 1, n minus 2. Always the penultimate shell is n minus 1. Whatever the valence shell will be n. So moving from the last one n, n minus 1 and n minus 2. The nucleus contains proton and neutrons. Neutron is chargeless whereas proton are positively charged. So the net charge of the nucleus is positive. Each individual electrons are negatively charged. There is an attractive force between the nucleus, positively charged nucleus, and the negatively charged electron. And there is another kind of interaction which occurs between the electrons present in one orbit and the other. Both are negatively charged, so repulsive forces operate. So these two kinds of forces operate in an atom. Okay, then which force contributes majorly to the shielding effect? The attractive force, that is, the attraction between the positively charged nucleus due to the positive charge of the net positive charge of the nucleus and the negatively charged electron results in attractive force. The more the number of shells present here, then more the number of shielding electrons. Okay, so that leads to the shielding effect. So note that shielding effect of the inner electrons on the outer electrons, that the valence electron experiences less attractive pull from the nucleus. More the number of inner electrons, then the pull experienced by the valence electron will be minimum, and as a result shielding effect will be minimum and the screening constant will also be minimum. The decrease in the attractive force reduces the nuclear charge. Okay? The more the attractive force, for example, the nuclear charge will be more. If there is a decrease in the attractive force, then your nuclear charge will be reduced. Here Z is represented by the atomic number of the element. Okay, you can calculate this effective nuclear charge using a formula. It is generally denoted by Z star. Z is the atomic number and star is the effective nuclear charge. It is calculated by the difference between the total nuclear charge and the screening constant. Screening constant is represented by sigma and total nuclear charge is represented by Z. So this difference will give you effective nuclear charge. Now, the periodic properties means you have to discuss how they vary along the period and along the group. Okay, group means vertical columns are called as group and horizontal rows are called as period. That we all know. So how many groups are in a periodic table? Like 1A, 2A, 3A, 4, 5, up to 7. So 7 groups are present in a periodic table. Okay, now look at this variation of the effective nuclear charge. Effective nuclear charge increases across the period, but when you design a group, the values of effective nuclear charge remains almost the same. This trend you have to understand. Now let's move on to the next property. Screening effect or sigma. Shielding effect or shielding constant is sigma. How it varies along the group and period. It's very simple. The only difference between The effective nuclear charge is it remains constant when you descend down the group. In the case of shielding effect or shielding constant, it increases across the period as well as across the group. That's all. To keep it simple. So greater the magnitude of sigma, greater will be the shielding effect because it's directly proportional. This is caused by the inner electron or intervening electrons on the valence shell electron. Okay, this is important topic, Slater's rule. For instance, in your exam, they will ask you to write about the Slater's rule. Like you have to list the 6 points given here, and also they will give an example like sodium atom or sodium ion. So you have to calculate the Z effective, that is effective nuclear charge for that particular atom or ion. So always there will be a confusion how to calculate the effective nuclear charge for an atom and ion, that we will discuss in the coming slides. Okay, now what are the rules? So there are three types of electrons. As you know, like we also got F shell, but sp and d. First, we will consider the situation or scenario for S and p valence electron. The first rule framed by Slater tells that you have to write the electronic configuration of elements of an atom or ion in the following order, mean increasing order of the shells. Okay, like 1s, 2, then 3, 4, 5. So this follows the Aufbau principle, as you know. And the maximum number of cell in a s orbital is 2, p orbital is 6, and d orbital is 10. That also you know. So when you write a shell like 1s, you have to write within the bracket. When both are in the same shell or same level, then you can put both within the bracket, like 2s, 2p, 3s and 3p, so on. Now, if it is s orbital, it is fine. The maximum number of electron is 2, so you can write 1s2. But if you write 2s and 2p, you have to sum up both and you have to write in the superscript. For example, maximum number of electrons in 2s orbital is 2, 2p orbital is 6. So 6 plus 2, 8, and 3s will be 1. This is for sodium. Now sum up all these numbers in the superscript. 2 plus 8, 10, 10 plus 1, 11. So this 11 corresponds to Z value, that corresponds to sodium atom. Atomic number of sodium is 11. If you write the configuration for sodium ion, then one electron will be removed. So the total number of electrons will be 10 in that case. Then 3s you have to exclude. This is the only difference between writing an electronic configuration for an atom and an ion. Okay, the second rule states that electron in a certain ns or np level is screened only by that particular electron that is present at the same level and by the electrons of lower energy levels of an atom. For instance, if you are calculating the screening constant for 2p electron, then how many electrons are here? 8. So when you calculate that 7 electron, whichever electron you are calculating, you have to exclude. That 7 electron screening, will be involved in screening, and the previous cell, that is 1s. So 7 plus 2, 9 will be involved in screening. Whereas 3s is the next shell, so it is behind. So it will not be involved in screening. So this is the point he made, and he made the clarity. Electron lying above Ns and Np. For example, in this case 3s1, it is the valence cell. When you calculate the screening shielding constant for this one p electron, you have to exclude this one because this will not be involved in shielding. Electron lying above Ns Np level do not shield any Ns Np electron to any extent. This is very important point. And electrons of higher energy levels did not shield the lower energy level of an atom. That is what he postulated, or he given in the third point. He has given in the third point. For calculating the value of screening constant of the valence electron of sodium atom, the electronic configuration of sodium atom, you write like this, and then shielding constant 3p electron, you can calculate as I told. Now, same point only he has given. with more clarity in the third one compared to the second one. The fourth point is very important. What Slater said, you have to give a numeric, that is, you have to give some value. For instance, ns and np you can give 0.35 and n minus 1 cell you can give 0.85, which is little bit higher, which means you are moving close to the nucleus, the value is increasing. That is logic, right? And then when you move to n minus 2, even further close to nucleus, then the charge will be, the value you should give more, that is 1 each. Okay, so these are the value 0.35 for the same one, previous cell n minus 1 0.85 and n minus 2 1 and so on. So this is an example where the effective nuclear charge Z effective for sodium atom is calculated. You can calculate this one. First, draw the electronic configuration. 2 electrons in n minus 2, n minus 1, 8 electron, and the valence cell 1. 2 plus 8, 10, 10 plus 1, 11. For the nth cell, as we discussed already, 0.35. N minus 1, 0.85. N minus 2, moving closer to nucleus, so higher value 1. Look at here from penultimate, that is valence cell, to the n minus 2, the value increases. Okay, this is for ns and np. So all you need to do, write the electronic configuration and then put the value, and then you can easily, you are calculating for this uh, s electron, so you have to exclude this one. So n minus 1 will be 0.85, am I right? 0.85 into 8, these 8 electrons, and then 2 into 1, so this is the value of 1, so you are doing this one. 2 plus 8 into 0.85, which is equal to 8.8, and z minus sigma, right? This is the value of sigma. So subtract this 8 minus 8.8 from 11, then you will get 2.2. So this is the Z effective of sodium atom. Now you can also calculate for a atom with D shell. So here we are going to include D shell. So the only difference is you will not have 0.85 value. Nth one will be 0.35 and all the lower lying orbitals will be having, shells will be having 1. So there is no 0.85. This 0.85 you will have for n minus 1 only in the case of s and p orbital. For d orbital, when you are having d orbital, all the lower lying orbitals will be having 1. Then you can easily write the electronic configuration 23 vanadium. So you can write this configuration and then you can substitute the values. Look at here, what is the 4s1? You are going to calculate for this one. Exclude that electron, because whichever electron you are calculating the sealing constant, that you have to exclude. So 1 electron, 1 into 0.35. This is the valence electron. So remaining, how many electrons you calculate? 2, 2 plus 8, 10, 10 plus 18, 18, 18 plus 3, 21. So you can substitute in this one and you can easily calculate. So individually they have put, but you can also directly, you can substitute this one and you can calculate the value. 23 minus 19.7, you will get 3.3 in this case. Okay. So in this way you can calculate for any electron. For example, if you calculate 4s electron, the rule will be different. If you calculate for 3d electron, it will be okay. Where you will get the confusion? For example, in your exam, they are asking calculate the screening constant or shielding constant for 4s electron. If 4s electron mean, then you should have 0.85. Look at here. For example, you are having 0.35, 1 into 0.35. 3d electron is the n minus 1, 3 into 0.85. So you are having 0.85. But the rest of this one you can put 1, right? So you can directly put this one. So this 3s and 3p, 3d are in the same level, am I right? So 8 into 0.85, 3 into 0.85, they carry the 0.85. But whereas the lower lying one, 8 into, that is second cell, 8 into 1 and 2 into 1. So you will get 19.7, you can subtract this one. And when they mention it is for 3d electron, then there is no 0.85. That is what I want to clarify here. when they mention screening constant for 3D electrons, then you should not include 0.85. When it is for S electron or the valence electron in the S cell, then you have to include the 0.8. I hope it is clear. So this one you see 2 electron into 0.35, and all the lower line one you can have the value 1, and you can substitute and it will be 18.7, and you can subtract this one and you will get the value final one. Easily you can do the maths and you can get the value. This is how the screening constant is calculated. Okay, now variation of orbital energies of atoms in the periodic table. So mostly, this is like an important one, but you can, understand about this one. But I would say compared to other periodic properties, this has least role, or in the examination point of view, they mostly, seldom ask this one, but still, you need to know the periodic properties. And it is also one among the periodic properties. So let's see how it works and how the property vary. So the energy which is essential to take an electron present in the orbital to infinity. So you have an orbital, you have the electron, you move the electron from that orbital to infinity. When you move that, there will be a release of energy, and when an electron from infinity is added to that orbital, an energy will be, energy exchange will be there, release will be there. So you have to understand this one. It is referred to the energy of the orbital. So based on this, the orbital energy can be arranged accordingly. The energies of orbitals of hydrogen and hydrogen-like particles, single electron, are dependent upon the value of principal quantum number, as well as multi-electron atoms depend on the principal quantum number and azimuthal. This we know that. Okay, so you got this. You see the energy level for 2s to 4s, there is a variation, but they are in the same, arranged the same group, you can say. And also, this will be for 4p and 4d, 3d, and 4, like that you can write. The lower value will be n plus 1, and for uh, orbitals, you can write like this orbital for a typical multi-electron thing you can write. So there will be arranged in a different order. Okay, what are the factors that affect the orbital energy? So the s orbital electron will be more tightly bound to the nucleus compared to the p electrons, because it's a spherical shape, it's a dumbbell shape, uh, which is more tightly bound in regard to a d orbital electron for a given number of principal quantum number. So the order will be s, p, and then d. Compared to p orbital, s electrons will have more negative or lesser amount of energy. Here the p orbital energy will have less energy than d orbital energy. Okay, extent of shielding from the nucleus is different for the electrons in different orbitals. It leads to splitting of energy levels that have the same principal quantum number. And orbital energy can also depend on the values, that is principal quantum number values, as well as azimuthal quantum number value, which are symbolized as n and l. So lower number means n plus 1 or l, and for an orbital the lower its energy. So when this value is lower, means the orbital energy will be lower. With an increase in the atomic number, the orbital energy decreases in the same subset. Electronic configuration of elements in the periodic table. I think electronic configuration you can write usually following the Aufbau principle. For instance, we will see how the electronic configuration in period. As you know, that period indicate the value of n for the outermost valence shell. In other words, you can say that successive period in the periodic table filling of next higher principal energy level, like n is equal to 1, n is equal to 2, etc. Group-wise electronic configuration. Elements in the same vertical column of group have similar valence electronic configuration, same number of outer orbitals, and similar properties. So S block, P block, D block, and F block depending on the number and type of atomic orbital. There are some exceptions, like helium belongs to S block, but its position is in the P block. Okay, so there are some exemptions. I'm not going to talk about the exemption in detail. The other one is hydrogen. Only one s electron, it can be placed in the alkali metal. So there are some anomalies. Okay, and electronic configuration, how you can write based on the Aufbau principle, and the filling of electron follows this order from 1s, 2s, then 2p, 3s, like that. The arrows have been indicated. I think you are well aware of this one. Based on this, you can write the electronic configuration. Atomic radius and ionic radius. So the covalent radius, there are three types of atomic radius. One is covalent radius, metallic radius, and van der Waals radius. For instance, covalent radius, it is defined as one half of the distance between the nuclei of two covalently bonded atoms like hydrogen. So this is covalently, the orbitals are overlap, and you have to calculate the distance between the two nuclei of these atoms, and the half will be the bond length. Covalent radius is nothing but 1 by 2 of the half of the bond length. The internuclear distance between two hydrogen atoms in the hydrogen molecule is 0.74. So this is the internuclear distance, which is the bond length. Half of this will be the covalent radius, 0.37 Armstrong or 37 ppm, parts per picometer. And van der Waals radii. So imagine two such hydrogen molecules. Okay, so this is also covalent bond is involved. Also covalent bond is involved, and they are overlap. So you calculate the half of the internuclear distance between nuclei of two non-bonded isolated atoms or adjacent atoms, and then the half will be the van der Waals radii. For instance, for hydrogen, the internuclear distance between two hydrogen atoms of the neighboring hydrogen molecule will be 2.4 Armstrong. That will be 1.2 Armstrong or 120 parts per picometer. And metallic radius. So it is half of the internuclear distance between two adjacent metal ions. For example, you are having, it is a metallic radius, so obviously in metal, so you got the two adjacent metal ions, and then the internuclear distance between them in the metallic lattice will give you the metallic radius. So obviously the van der Waals radius will be more, metallic radius will be followed by metallic radius, and then covalent radius. So we will discuss how they vary along the period and across the group. Okay, periodic trends. Atomic size variation in periods. Obviously, when you move from left to right, the atomic size will be decreasing. Atomic radii or the covalent van der Waals radii decreases with increase in atomic number in a period. And also there is another thing called atomic radius factor A, or atomic radius is inversely proportional to 1 by Z effective, and the other thing is in a group atomic radius is directly proportional to the number of shells. So this is like a hint. Okay, look at here from sodium to chlorine, the atomic radius is decreasing, and also when you move along the group one lithium to sodium, the atomic radius is increasing. So group atomic radius will increase. Period. Look at here 152 to 66, 186 to 104. That is why oxygen is highly electronegative because of the smaller atomic size. Atomic radii, that is covalent radii, van der Waals radii, everything will be smaller for oxygen. Now, atomic size variation in group. When you move along the group lithium to cesium, the atomic radius will be increasing 152 to 262, and chlorine to um, chlorine, bromine, iodine, actinium also same thing. And also atomic radius along the group, it increases. The simple example you can see that like pots arranged one above the other, you can have the larger one, and then when you go on top it will be smaller. Same thing follows here. When you move from top to bottom, the radii will be increasing, like lithium, sodium, potassium, rubidium, the alkali metals. The radii increases along the group. Ionic radius. Ionic radius is the distance from the nucleus of an ion up to which it has influence of the electron flow. So in this case, an electron has to be removed. The removal of an electron from an atom results in the formation of cation. Whereas anions are formed when an atom gains an electron. So there is a difference between anion and cation. So the size of the cation, since you are removing an electron, is always smaller than the neutral atom. That makes sense because the effective nuclear charge will be more. While the size of the anion is always larger because you are adding one more electron, repulsion will be more. Effective nuclear charge will be decreased. Sealing constant will be decreased as well. So as a result, the charge of the neutral anion will be larger. Okay. Size of the cation will be smaller than neutral atom, whereas size of the anion will always be larger than the neutral atom. So generally, ionic radii of the elements exhibit same trend as atomic radii. It decreases from left to right and increases across the group. Okay. So there are some species like isoelectronic species, atoms and ions which contain same number of electrons. For example, oxygen, as you know, atomic number is 8. O2 minus anion means 2 electrons are added. So 8 plus 2, 10. Fluorine atomic number 9. 9 plus 1, 10. Sodium atomic number 11. 1 electron is removed. So 10. Magnesium, 2 electrons have been removed. Atomic number is 12. 12, right? 10 plus 2. Like that. It can vary. So same, all of them have same atomic number. For example, 12 here, 2 plus means 2 electrons will be removed. So atomic number of magnesium is 10. Next to sodium, right? So how atomic and ionic size varies? This picture gives us an idea. Like lithium to rubidium, it increases from 0.68 to 1.47. Same thing. Check every group or each group 0.31 to 1.13, 0.23 to 0.81. So it is increasing. But if you move across the period 0.68 to 1.33, and 0.97, 1.8 atomic size. Okay, so you can get an idea. So this is particularly in generally, if you move along the period for the atoms, it will be decreasing, but here they are ions. So as a result, when you move from lithium to fluoride, this is cation, this is anion, the charge is increasing, size is increasing. Sodium to fluoride, again it is increasing. Compared to cation and anion, size is larger. Remember that one. So here also, compared to cation, anion size is larger. Same trend is followed. I think I will finish with this one, and then the remaining properties we can cover in the next lecture. So I will stop with this one. So among the 6 periodic properties, we have covered 3 in this lecture. I would like to discuss the 3 other periodic properties in the next lecture.